Good afternoon, everybody. Welcome to the 2025 Durand Lecture for Public Service. My name is John Rose, and I co-chair the Public Policy Committee Honors and Awards Working Group. The Durand Lecture for Public Service emphasizes notable achievements by a scientific or technical leader whose contributions have led directly to the understanding and application of the science and technology of aeronautics and astronautics for the betterment of humanity. This premier lecture is named in honor of Dr. William Durand, who was a U.S. naval officer and a pioneer in mechanical engineering. During Dr. Durand's remarkable 99-year life, he contributed significantly to the development of aircraft propellers. He was the first civilian chair of the National Advisory Committee for Aeronautics, or NACA, the forerunner of NASA. The Institute's Public Policy Committee takes pride in selecting accomplished leaders in aeronautics and astronautics who can share their knowledge through the Durand Lecture. The 2025 Durand Lecture for Public Service is awarded to an internationally recognized expert in hypersonic aerodynamics, propulsion integration, and vehicle design and optimization, Dr. Kevin G. Bowcutt. His lecture is titled The Evolution of Hypersonic Flight Over 7 Decades and the Technical Breakthroughs That Got Us Here. A little background on Dr. Bowcutt. He is a Principal Senior Technical Fellow and Chief Scientist of Hypersonics for Boeing with 42 years of experience. He is an AIAA Fellow. He is also a Fellow of the Royal Aeronautical Society and a member of the National Academy of Engineering. In 2021, he was selected by Texas A&M to be a Fellow of Hagler Institute of Advanced Study, and he holds BS and MS and a PhD degrees in aerospace engineering from the University of Maryland. Dr. Bowcutt leads Boeing's hypersonic vehicle advanced design and technology development efforts. Today's lecture will chronicle the major milestones that have enabled air-breathing hypersonic flight, bringing future promise to current capability and leading to worldwide pursuit of hypersonic capabilities and leadership. Hypersonic flight has the potential to dramatically impact national defense and significantly improve the speed of global travel and the frequency and cost of space access. We are looking forward to hearing from Dr. Kevin Bowcutt. If time allows, we'll have a question and answer session after this lecture. Please refer to the QR code on the screen and submit your questions, which it'll be up there shortly, and we'll try and pull from those at the end. So Kevin, if you want. So now please join me in welcoming our distinguished lecturer to present the 2025 Durand Lecture for Public Service, Dr. Kevin Bowcutt, and his lecture, The Evolution of Hypersonic Flight Over 7 Decades and the Technical Breakthroughs That Got Us Here.
All right. It's going to be fun. First of all, thank you for coming, and thank you to AIAA, John and Mark Lewis, who nominated me, and all those who were involved in my nomination and selection for this award. I'm very honored. I've had a 40-year career in hypersonics that's been thrilling. I've seen a tremendous evolution in the technology and capability. I'm going to share some of that with you today. I also want to thank all my colleagues I've worked with over those 40 years, colleagues and friends that have joined me on this adventure. It's been a thrilling ride, and I really appreciate and value all their contributions. And my colleagues and friends, some of who were in the audience, who contributed some really cool material for my slides. So with that, I'll get started, and I'm going to do my best to leave a little bit of Q&A time. I do love to talk about this, so I could talk about it forever. I'll do my best. All right, the age of hypersonics actually began 76 years ago, almost 76 years ago. It was on February 24th, 1949, where the U.S. Army took a captured V-2 rocket, stuck a WAC Corporal second stage on it, launched it out of White Sands missile range. Both stages went out of the atmosphere, and when the second stage re-entered, it was going somewhere between Mach 7 and Mach 8, depending on what the atmospheric temperature was at the time when it hit continuum flow. That was the advent of human hypersonic flight. Since that time, over the next about 50 years, hypersonics was relegated to being propelled by rocket engines. That's the only way we had to do it, which is great, and it allowed us to do a lot of things, but it also has some limitations. So in that period of time, we had the rocket-powered X-15 that went Mach 6.7. Some of people earned their astronaut wings flying that aircraft. We, of course, had ballistic reentry vehicles. Have I lost my mic? I think I lost my mic. There we go. We're back. Ballistic reentry vehicles, reentry speeds. The Apollo space capsule went Mach 37 on a return from the moon. course, the space shuttle, last flight in 2011, all this is powered by rocket engines. Again, rocket engines are great, but one of the things that we would like to do is get from point A to point B in the world faster than we currently can at about Mach 0.8. Again, rockets can do that, but there are some limitations, kind of illustrated here. So on the right, we of course have ballistic flight, the type of flight that typically takes us to space. That requires going about, even to get anywhere in the world, any long distance across an ocean, you're going to go about Mach 25. That comes with extreme aerodynamic heating and temperatures. There are also human factors involved. If you were to fly in a rocket, you're going to pull quite a few G's, and you're going to experience weightlessness. That's not comfortable for everyone. Certifying vertical takeoff and landing for, say, commercial operations could be very challenging to get 1 in 10 to the 8th or 10 to the 9th probability of a catastrophic failure. I hope we can do it, but it'll be challenging. And high ticket cost. If you take an example, round numbers, if you had a rocket that cost $50 million and you had 500 passengers, that'd be about $100,000 per ticket. Now, if you could get the cost down to $5 million, that's $10,000 per ticket, and now you're in the realm of what's reasonable. The other way you can do it is boost glide. You can rocket boost to high speed and aerodynamically glide. And what you see plotted here is how far you go as a function of your boost speed. And for lift-to-drag ratios of 3 and 4, which are practical when you get up into that high-speed range, and you have to have blunt noses and leading edges to withstand the aerothermal environment. Those create drag, hence reduce lift-to-drag. So that's a practical level up at those very high speeds. And what you can see is going across from the U.S. East Coast across the Atlantic, about 2,500 nautical miles, you have to go about Mach 15 to 17. And to go across the Pacific from the U.S. West Coast, you have to go between Mach, say, 19 and 21, depending on your L over D. These are very high speeds. It takes a lot of propellant to get to that speed, and you're in this regime where the surface temperatures get to thousands of degrees. So now you have to have different kinds of materials, typically ceramic materials, that are not necessarily easy to build and not necessarily affordable to build as well. So it's a very challenging regime thermally. The other way you can do it is to cruise at hypersonic speeds in the atmosphere. And what that avoids is you can have an average speed or a constant speed that's equivalent to an average speed much higher, or a constant speed that's equivalent to the average speed of, like, say, boost glide or ballistic. And doing this, being at a lower speed, say Mach 5 or Mach 6, you're in a much more benign, it's still hot, it's still very hot, but it's a much more benign aerothermal environment. You can go from ceramics to metals, to even titaniums or nickel-based metals to survive that environment. The key to that is air-breathing propulsion. You don't carry your oxidizer, you use the air to oxidize your fuel. And that efficiency is reflected in this curve called specific impulse. Fancy word, but it just is equal to the thrust divided by propellant flow rate. So what you see in this plot is specific impulse as a function of speed for four different propulsion systems and 2 different types of fuel. You see the rockets, because they have to carry their oxidizer, they're in the range of 450 seconds and below. Air breathers can be up, a modern turbofan engine that you flew here on cruises with about 7,000 seconds of specific impulse, even using hydrocarbon fuel, okay? So a couple of things, you see much higher specific impulse, you see higher for hydrogen than for hydrocarbon, and you see a decay with speed or with Mach number. Now the reason hydrogen is higher, it has more energy per unit mass, and that just naturally makes the ISP higher because, again, thrust per unit mass flow rate. However, it has less energy per unit volume. So if you use hydrogen, it's a much more voluminous vehicle. The vehicle is going to have more volume, it's going to have more drag associated with it, so it has its challenges. And it's cryogenic, and you have all the issues associated with that as well. You also notice the decay in thrust, or ISP. Why is that? It's simple physics, and you can't get around it. The faster the air is going, the smaller the pressure rise when you add a unit of heat. So when you burn it, you're going to get smaller and smaller pressure rise. Well, thrust is pressure acting on the metal of your engine, so your thrust goes down. If your thrust goes down, your ISP goes down in proportion to it. What does this mean as you go to these, trying to push to these hypersonic speeds? It means that your engine has to get proportionally bigger to have adequate thrust to propel the vehicle, and I'll talk a little bit more about that in a minute. But a bigger engine means a bigger inlet, a bigger nozzle. Those things, unless they're operating on design, create drag, and so you'll have more drag. So it's quite a challenge to integrate this relatively larger engine on an airframe to fly at hypersonic speeds. Okay, so I'll talk more about it in a minute, but the idea of air-breathing hypersonic flight, Mach 5 and above, came about in 1958. Some NACA researchers, Weber and McKay, who came up with this idea of, hey, could we burn in supersonic flow? And since that time, it took us about 50 years to prove that technology, and I'll explain a little bit more why later. It's very challenging for a number of reasons. But over that period of time, we finally got to the point where in 2004, we flew the X-43, NASA did, Boeing helping them, and we proved that scramjets could indeed generate thrust in flight and be a practical propulsion system. Then in the 2010-2013 range, we flew the X-51 with the Air Force and participation of DARPA and proved that hypersonics could be practical. And since that time, we have hypersonics, air-breathing hypersonics in the form today, for good or bad, air-breathing cruise missiles that fly at hypersonic speeds. And we have the technology to now, and a lot of people are looking at hypersonic reusable flight in the form of point-to-point travel and even access to space using more aircraft-like approaches to getting to space. Now, I know from my 40 years experience that hypersonic vehicle design is really fun, and it's really fun and interesting because it's really hard and very challenging. And it's challenging for a number of reasons, a few of which I summarize here. And I'm going to talk a little bit about each of these challenges before I talk about kind of the advancements we've made. So aerodynamic behavior varies extensively with speed because the physics of flow changes with Mach number from subsonic to transonic, supersonic to hypersonic. That changes the aerodynamic behavior of the vehicle. Air-breathing engines, you can't just have one. You can't take off on a ramjet or a scramjet, and a turbine engine can only go to about Mach 3. Maybe it could be pushed to Mach 4. So it requires more than one engine or combining engine cycles. Of course, due to frictional heating, the outer structure gets very hot, particularly leading edges, but you're dealing in a very hot regime. It means different types of materials. The vehicle has to carry a lot of fuel. No matter what, the drag is higher. You've seen the ISP is lower. It's going to burn more fuel. We typically have to have about 50 to 80% of the mass of the entire vehicle as propellant or fuel. That impacts the shape, the size, et cetera. Testing limitations, this regime, there's a lot of energy and there's a lot of temperature involved with it. So if you try to take air and blow tens or hundreds of pounds per second of air at thousands of degrees, requires a tremendous amount of energy, and the environment inside the wind tunnel is extremely hot. It's very challenging to do. So it limits what we can do on the ground. It's also challenging to fly fast because there's a lot of energy, it requires a lot of fuel, and there's just a lot of uncertainty in the environment. So it makes it more challenging to develop a hypersonic vehicle. So how do we do our best in those areas, and where we fill in the gaps is with our modern computational tools, which are very powerful tools. And so through modeling and simulation, we can fill in the gaps, and we're getting more and more capable in that area, as I'll illustrate in a minute. There's also a lot more uncertainty that we have to live with, and the question is, how do we live with that uncertainty? How do we accommodate it? And I'll talk about that. Vehicles must be highly integrated. Everything, you know, you're basically operating on relatively small margins, and everything interacts with everything else. So it has to be very highly integrated to make the whole system work together. Every component, every discipline, aerodynamics, propulsion, thermal structure, stability and control are all heavily interrelated and interact with each other, and often in nonlinear ways, which makes it quite challenging. And we have a method that we've developed over the past about 25 to 30 years called multidisciplinary design optimization, which helps accommodate that high degree of integration. So here's an example of that aerodynamic behavior as a function of Mach number, again, because the flow physics changes with speed. What you see on the left is the drag, coefficient of drag profiles with speed, the well-known drag rise, the transonic drag rise. There's a similar effect on the lift curve slope in the lower left. That also varies dramatically, so the lift and drag varies dramatically with speed. On the right, you see longitudinal and lateral directional stability and curves, and you just see a lot of variation with speed. On the stability side, it's challenging because if you want it to be stable everywhere, like a certified airplane has to be, it's probably going to be too stable in some regime. And in that, if it's too stable, it means you can't move it. You can't maneuver. You're kind of stuck if it's too stable, or it takes a lot of power to maneuver the vehicle. If you let it be unstable, maybe it's too unstable, and you have to deal with that. But today, we have very powerful tools in computational fluid dynamics and optimization. This is an example of multi-point optimization, where we've taken the takeoff condition, transonic condition, and a hypersonic condition, and optimize the aerodynamic shape to behave well in all three. And the net result is good aerodynamic behavior across the speed regime, as well as good stability behavior across the speed regime. Longitudinal stability happens when your slope in moment with angle of attack is negative, a downward slope as you see on the left there. So you see in most Mach numbers, we're positive to neutrally stable through the normal operating range of the aircraft, at least at high speed. And then on the right, where you might take off at maybe 10 or 12 degrees angle of attack, you can see that dark blue line, it starts to become neutrally stable. Much more a vehicle shape that can behave much better across the entire regime through this multi-point optimization. Getting back to the propulsion side of things, I mentioned you can't just use one engine, and it's the thermal limits that prevent that. So typically a turbine engine has turbo machinery elements inside. Thermally, they can withstand up to about Mach 3 operation. And with modern technology, we may be able to push that a little bit, but that's about the limit. You just run out of thermal capability of that turbo machinery inside the engine. So what do? We remove it, and we create a ramjet engine. We use shock waves and an inlet shaping to compress the flow. And we ultimately go through a terminal or a normal shock, drive the flow subsonic, add fuel, and you get thrust. But that has a thermal limit as well. As you go up in speed, that last terminal shock creates very large total pressure losses, very high static pressure gains, and very high static temperature gains. At some point, the temperature gets so hot that you'll dissociate the air, and even the fuel you inject in the air. And if the whole idea of fuel is to form products like CO2 and water, and if instead you dissociate it, you're not going to create thrust. And so how do you combat that? Well, let's remove that terminal shock, and that's what Weber and McKay, that was their idea. Remove that final shock wave, let the flow stay supersonic, and try to mix and burn fuel at a supersonic flow state. Now, that is a very challenging thing to do. The air inside of a scramjet engine is typically there for about 1 millisecond. So think about it, in 1 millisecond, you have to mix all the fuel and air molecules, you have to get the ignition chemistry to happen, and then you have to have that combustion complete the process, so you have fuel products at the end, all of it in 1 millisecond. And it's the challenge of doing that in a way that doesn't create too much drag and take away from your thrust that made scramjet engine design very challenging, as well as the fact that the inlet has to compress the air efficiently and the nozzle has to expend it efficiently. That was very tough to do, and it took us 50 years to master that, of a lot of R&D. Now, so how we fly typically from, say, a takeoff condition to a hypersonic condition is we have to combine. We either have to use 2 different engines and shut one off and turn the other one off, or we blend them in some way. The SR-71 actually did that in a form of a turbo ramjet, where it's got a turbojet combined with some air bypass. So as the speed went up, more and more of the air was bypassed around the core, dumped into the afterburner, which is essentially a ramjet. A way to get faster than the SR-71 engine is turbine-based combined cycle, where you have a turbo fan, say a low bypass turbo fan, and a dual mode ramjet over under side by side with variable inlets and nozzles that direct the flow through the turbine engine at lower speeds and then through the high-speed engine at higher speeds. And there's lots of variations on these themes. There's lots of different innovative ways to combine turbo machinery and non-turbo machinery engines with other elements like cooling and so forth to achieve hypersonic flight. Now, going back to the origins of the scramjet engine, again, Weber and McKay, 1958 from NACA up in Cleveland, the NACA facility there, now called NASA Glenn. They came up with this idea, and you can see from their report some of the things that they mused about, the challenges that they foresaw in doing this. And then, but at the bottom, however, the trends developed here indicate that it's possible, and we've now, after 50 years, proved indeed that it was. Some of the early pioneers in this field were from Johns Hopkins Applied Physics Lab. One of those pictures is of Fred Billig. He was one of my mentors. He was an adjunct professor at University of Maryland and taught me about hypersonic propulsion. That's where I learned it from. We had the General Applied Science Laboratory, founded by Antonio Ferri. He was a key leader in the field at the time. And then NASA Langley and Glenn were heavily involved. The NASA HRE engine you might be familiar with, going on into the 70s with the engine you see on the lower right. And a couple of the early companies, Marquardt, Garrett, and GE, that all participated in the early days of scramjet engines. Now, it's one thing to have the engine. I told you how highly integrated the vehicle has to be. And as for the reasons of this balance between thrust and drag. So one of the things I mentioned that as the thrust goes down, you have to make a bigger engine. The thrust per unit airflow goes down. You have to have a bigger engine to keep the thrust up. The reason why that's important is this quantity called thrust to drag ratio down here. So I mentioned, a specific impulse determines the amount of propellant you use to accelerate over a given speed range, okay? But in an air breather, it's not just the engine ISP, it's the net ISP. So that's what we call effective ISP. It's the net thrust minus drag over propellant flow rate. A little bit of simple algebra will take that thrust minus drag over propellant flow rate, and it turns into that equation there for effective ISP. It's the engine ISP times 1 minus 1 divided by thrust to drag ratio. So you see that if the thrust to drag ratio is 2, you're going to lose half of the engine ISP in the effectiveness, so you're going to use more fuel as a result of that. The bottom line is you need a thrust to drag ratio of about at least 2, in the 2 to 3 range. The knee in the curve and the fuel use curve occurs between a T over D of 2 and 3. So bigger engine, get a big engine, and you look at the aerodynamics of hypersonic vehicles. They're highly swept wings, sharp leading edges. You start blending them together, and you get very distinct, different looking vehicle shapes than you're used to seeing as airplanes. And a few examples are represented up above there. They basically become flying engines, okay? So it's very important that you integrate them in a way that minimizes the drag contribution, so you keep that T over D high. You have to worry about the inlet operating efficiently, high compression efficiency with low distortion over a broad Mach range, which typically involves some variable geometry, unless the Mach range is small. Same thing on the nozzle side. And it turns out, optimally, the propulsion system, as your lift-to-drag ratio goes down aerodynamically, you should optimally get some of your lift from the engine. It's not just thrust, it should produce about some of your lift as well. For an L over D in the 5-ish range, about 15%, 15 to 20% of your lift should come from the engine. So it affects how you design the vehicle, how you integrate it, so it all together you're getting good aerodynamic performance, good propulsive efficiency, and some lift from the propulsion system. Switching over to the thermal side, this is a plot of the surface temperature, what we call radiation equilibrium surface temperature, as a function of speed for an 8-degree surface. Now, hypersonic vehicles, ones that are meant to fly through the air, have to be very slender, and they're slender in the sense of having low impact angles on their surfaces. Typical angles are going to be 4, 5, 6, 8 degrees in that range. So I took the extreme end of 8 degrees here and plotted what the temperature is. Now what radiation equilibrium means is you've got aerodynamic heating going into the body, and then you've got radiative cooling going out. It's emissivity times Stefan Boltzmann's constants times T to the 4th. That's the radiation energy out. When those balance, that's the temperature that surface will see. So what you see here is in the kind of the pink-purple line, that's turbulent flow, and below that is laminar flow. And you can see in the Mach 5-ish region, that's about where the limit of titanium use. From there up to about Mach 7 and 8, nickel-based metals like Inconel can be used. Beyond that, it's refractory metals or ceramics. And I'll show you another slide in a minute. So that just gives you a sense of what you have to build and the kinds of temperatures you're dealing with as you go faster and faster in speed. The other thing to point out is that laminar line. There's 5 up to 8 times less heating if the flow is laminar on the surface. That's very significant, and the friction's less as well. So if you could keep it laminar, that's great. Now, flow is naturally more stable the higher the Mach number. So if you start flying in those higher Mach number regimes at altitudes above about 100, 110, 120,000 feet, you can get into a regime where significant run of flow is laminar. And you can see there's a great advantage to that. It could change the materials you make it out of. It could change the drag of the vehicle through the friction, et cetera. And one of the things we've learned over the past 30 years is much more, it's a very complex problem, this boundary layer transition. Over this time, we've learned a lot more about the physics of the transition processes, of which there are many, and we've learned how to predict that transition between the two quite a bit more, and I'll show a little bit of an example of that in a moment. But a very challenging environment to design in. These are the kinds of materials we use to deal with those environments. Like he said, titanium up to about 650 C, nickel superalloys up to about 900 C, refractories can go to 1400, but they're very dense, very expensive materials. They're typically only used in small regions where you really don't have other options. And then you get into the ceramics, like oxide-based and carbon-based ceramic matrix composites, and that'll get you up to about 1500 C, and carbon-carbon up to about 2500 C. There's a lot of research going on in this area too. We've got very powerful tools in this area, even up to quantum computing, where we can explore lots of combinations and model materials. And there's an area called materials, a class of materials called complex concentrated alloys or high entropy alloys that could enhance our temperature and or strength to weight capabilities of materials. There's also active cooling approaches. From one of the things we typically do in scramjet engines is the walls or heat exchangers and use the fuel to cool them before the fuel's burned. You can use that same approach anywhere on the vehicle. You just have to remember at some point you're going to run out of cooling capacity of the fuel that's on board. You could add other fluids like water, say, and you could use it for regenerative cooling like that, or even through film cooling or transpiration cooling where you're ejected. But just keep in mind, if you consume that fluid, it goes into the denominator of the ISP equation. That's part of the flow rate that's leaving your vehicle, the mass flow rate. So it effectively reduces your effective ISP and will use more propellant, so to speak. There's also heat pipe technology, which is a closed loop system that takes heat from, say, a stagnation point, transfers it back to a cooler area where it can radiate, and that's through a working fluid condensation process. Mention ground testing. So the desire to fly fast has inspired our nation to build hypersonic tunnels starting back in the 1950s. We do have a lot of capability. Again, it's hard and it's challenging. We can't do everything, but we can do some things. I don't have a lot of time to go through all these examples, but just the essence, there's different ways to do this. We have continuous flow facilities like at ADC. Those tend to be warm to slightly hot. They're not necessarily true velocity, but they match the Mach number. We have blow-down facilities where you pump up big tanks with pressure, and you blow them down, and you might heat them a little bit, or you might heat them all the way to the actual temperature of the total temperature of the air. And those are true enthalpy facilities. ADC Tunnel 9 is an example of that. The NASA 8-foot tunnel actually burns the air using methane and then replenishes the oxygen to get the right oxygen ratio. So you can get true enthalpy, but now you've got water and CO2 in the flow that you wouldn't have in free air. We have shock tubes like the very capable Kubrick Lens 2, true enthalpy facility, very high Mach numbers. You know, it used to be the realm where we could only get a millisecond or two. The technology has evolved to the point where we can get like 300 milliseconds, which seems really short, and it's short, but that's a lot of air flowing past the model at hypersonic speeds. We got quiet wind tunnels using Ludwig tubes. Several exist and more under construction. These have, they have designs that keep the boundary layer on the nozzle walls laminar, which then avoids radiation of noise down on the model and makes the environment more like you see in free flight. And transition from laminar to turbulent flow will occur in a more natural way. We have expansion tubes, which can get to very high speeds. We've got arc tunnels that electrically heat the air and can get up to reentry enthalpies to test materials typically. We've got gun ranges, and there's this new facility called the Phoenix J5 at ADC that is trying to take the idea of the Langley 8-foot, but do clean air, not burn the air, but blow the air through some kind of a heated bed of material that picks up the heat and then can be a clean air facility. So a lot of capability exists in the country and more is being developed. The other area that's advanced that has greatly enhanced our knowledge and ability to model, understand the flow and model it is instrumentation. You can see examples here, a large set of examples of laser-based instrumentation measure things like temperature, flow velocity, density, and species concentrations. So now, instead of just measuring pressure, temperature, heat flux, maybe friction, drag, shear on the surface, we can measure the quantities in the air itself. The example shown here is from Tunnel 9 using FLEET, the femtosecond laser electron excitation tagging approach. To measure velocity, you can see how it matches very well the predicted velocity profile of the tunnel with time. And in the lower image there, that's a time-dependent FLEET. You're getting lots and lots of images there. In the early part of that run, you can see the time running up to just below a second. And on the right is the wall. So it's kind of 90 degrees rotated. On the right is the wall. To the left is getting out to the free stream flow of the tunnel, and you can see snapshots of the turbulence in the tunnel boundary layer here. You can actually measure and quantify then the average and fluctuating velocity, and you can quantify what the turbulence levels are. So we have data now in the flow, we can better understand the physics of the flow, and we can use this data to improve our models, like the turbulence modeling that goes into RAND solutions. Flight testing is also advanced. This is a program that went from 2006 to 2017 called HiFire. It involved the Australians and the US. Boeing was a key player in this. We helped formulate, we invested in the project, we were involved in the whole thing. This was an attempt to fly faster and more affordably. We did experiments in boundary layer transition, in unique scramjet designs, in flight control, et cetera. And what has evolved, or what's followed after this, are things like the Bolt 2 flight experiments. I know some in the room, Bolt 1, Bolt 2 flight experiments, and the current program in the US called Mach-TB, which is using sounding rockets, orbital rockets, fighter aircraft, old fighter aircraft, and Stratolaunch's new Talon to do more rapid, more routine flight testing in the hypersonic regime. CFD has evolved tremendously over the last 40 years. It's kind of funny in the lower left there, even though this came from Grant Candler, graciously provided this. In the lower left, that could basically be my 1984 CFD class project, where we had to write a finite difference code, shock-fitted Euler solver for a hemispherical nose cap, and did that in class. And we've gone from that capability with maybe 1,000 grid points, following Moore's law, basically tracking Moore's law. We can have over 1 billion grid cells today. Back on the NAS program, which I'll talk about in a moment, around the 1990, a little before, right around the 1990 time frame, it was the first time where, again, all these uncertainties and difficult in testing, we pushed the CFD technology so we could actually use it in design. And back then we used RANDs to help us in the design Euler and RANDs analysis to help us in the design process of the NAS program. But since then, we've gone from RANDs to LES to DES to DNS, large eddy simulation. We can today, on limited scales and Reynolds number ranges, we can do what's called direct numerical simulation, where there's no modeling at all. You're solving the Navier-Stokes equations down to the smallest scales of fluid dynamic behavior. And you can see that progression of technology and algorithmically and grid generation-wise over that period of time. On the right is a good example. This is a Bolt 2 flight experiment from a couple of years ago. It was a boundary layer transition experiment. It followed after the HiFire transition experiments. This is a good example of the convergence between flight testing, between ground testing, and computational technologies. That vehicle was tested in the Kubrick lens. It was tested in the Quiet Tunnel at Purdue and other tunnels as well. It was flight tested on a sound rocket very successfully and had this very sophisticated computational fluid dynamics solutions of the flow field, and for the purposes of understanding the transition mechanisms from laminar to turbulent flow. Now, after all that, after all the testing and analysis, there's still uncertainty left over. How do we deal with that residual uncertainty? One of the ways is with adaptive flight control. This is a technology that Boeing has been developing for a couple of decades very successfully and has actually applied it on flying things. It's very applicable to hypersonics. You can see examples here. Two big areas of uncertainty are how the propulsion system behaves, how the inlet's very complex flow field with shock waves hitting boundary layers and very complex. When does that start and unstart? And you can see a hysteresis loop there of the inlet starting and unstarting process. How do you deal with those kinds of uncertainties in flight? Aerothermal elasticity is another one, where the interaction between aerodynamic forces, aerodynamic heating, and the thermal response of the structure, and how those interact, not only in terms of what it does to lift drag, but also pitching moments and stability and control. We can accommodate those kinds of uncertainties in using a technology called adaptive flight control. And Boeing's done a lot of that work to do that, and is actually starting to demonstrate it in the hypersonic regime. I talked about the high degree of integration, how hard, how challenging that makes hypersonic vehicle design. If all the parts of the vehicle are somewhat independent, like the wing's the wing, you can design the wing, and you can design the body, you can design the engine, you can kind of bolt them together with fairly minimal interactions. A hypersonic vehicle is not like that. Everything affects everything else, and they're typically very non-linearly related. And so how do we deal with that? We deal with that through what's called multidisciplinary design optimization. The key to this is being able to define a vehicle in a parametric way, its geometry, its shape, its configuration. So at Boeing, over the past 25 years, we've developed a tool called GUI-Duck that allows you to put a vector of design parameters. It could be 25, 50, or 100, and you instantly get a vehicle geometry out of it. The other part is tying together all the analysis tools and automate them so you don't have humans in the loop passing input and output data, but linking all the tools all the way from engineering analysis tools to computational fluid dynamics to finite elements, linking it all together. We use a commercial tool called Model Center to do that. And then once you've done that, and then optimizing in that space, searching for design variables that give you the best version of that vehicle. There's a number of ways to do that. You can use gradient search, you can use genetic algorithms, annealing algorithms. The approach that we typically use is a statistical approach where we use a statistical sampling of design space. So it's N vehicle designs scattered through design space. We analyze them using that automated analysis process. We take all that data, we fit it in a response surface model or a curve fit, and then we optimize on that space and then kind of converge on that loop. It's very effective. I started on the NAS program because it was so hard to design and we had a hard time closing on it. I started to play around with these MDO techniques, and I was fascinated by them because they produced non-intuitive solutions that were just really fascinating, because we had spent years hammering away at this design and we couldn't get it to close, and we thought we knew what affected what, but when we applied MDO to it, suddenly we found these very non-intuitive results that came out that we would have not have guessed. And why? Because of those interactions. This affected that, that affected that, and your brain can't process that, can't filter through all that, but these automated processes can find those solutions. From there, started to apply it to what became the X-51 very successfully. The X-51 was designed using MDO, and then since then we've gotten very much more sophisticated. Till today, we can take a vehicle with our best knowledge and experience and design it and analyze it, and we can still exceed that performance by 30% or more using this design optimization process. So it's very powerful, and we use it extensively. Now a little bit about my personal journey through this. So I came on the scene 1984, started my PhD program at the University of Maryland under Dr. John D. Anderson Jr. If any of you have had an aerodynamics class, there's a pretty high probability you used one of his books, textbooks for that class. So under his tutelage and mentorship, we were at the point now where we went from undergraduate. I had punch cards. I programmed, Fortran with punch cards. We had Textronic screens where we could actually save a file. So what I did was I took rudimentary forms of CFD, rudimentary forms of parametric geometry generation, and mathematical optimization techniques, combined them together, and my job was to try to find aerodynamic shapes that performed better than the state of the art. And it worked, and I found shapes that performed quite a bit better. They're called wave riders. And it was pretty exciting, and as I finished that work, right at the time I finished it, all of a sudden President Reagan and Ash announced that the country was doing a program called the National Aerospace Plane. So I went to work on the National Aerospace Plane for about 7 years and tried to help them design a single-staged orbit vehicle, given the tools I had learned from Dr. Anderson and my PhD program and Fred Billig at APL. So the NAS program. So the attempt here was a horizontal takeoff and landing aircraft that used air-breathing propulsion and flew all the way into orbit. It was exciting. The thought of doing this as a 25-year-old at the time was thrilling, and I was going to go in and help conquer this problem. And I learned a lot. I really cut my teeth on it. But what we discovered a lot of things through this. One of them was a single-staged orbit is not possible. It wasn't then, and it still isn't today. A technology can evolve to the point where it is possible. We're getting closer, but it's still not possible today. But we did learn a lot. We learned how to design air-breathing hypersonic vehicles. That's where the MDO, I first started to play with it and saw its power. We learned how to design viable scramjet engines. What we learned about scramjet engines in this program flew on X-43 by NASA. A lot of tech and high-temp materials and structures. CFD, I already mentioned. We got CFD to the point where we actually used it in design. We were kind of forced to. We had the tech was advanced, pushing it so we could actually use it in design in a rudimentary way, but still pretty sophisticated at the time. I mean, we had finite rate chemistry. We had everything we had to have at the time. And it added tremendously to the scientific body of knowledge and also trained a generation, including myself, in hypersonics. By the way, when I started here, it was kind of fun because I see myself as being on like the middle of the bridge. All the prior hypersonics from X-15 to Apollo to Space Shuttle, even XB-70, I got to work with the people that did those programs. They were my mentors. They were the people that trained me in this process, and then I got to go forward as kind of the new generation. That was pretty cool. Another thing, so at the end of this program, we still, to my dismay and the dismay of many, we still had not flown Scramjet. So this guy named Dr. John Hunter from Lawrence Livermore National Laboratory built this light gas gun. Light gas means low molecular weight. Hydrogen was the propellant, right? And why? The speed of sound is high because the molecular weight's low. The lower the molecular weight, the faster the speed of sound and the faster you can shoot a projectile. So he designed this cannon to demonstrate you could shoot something into orbit. That was his objective. He had it built. He said, I think it could also be used on UNAS program to test hypersonic things. So it came to the program, it flowed to me, and I looked at it and I was like, maybe I could shoot a scramjet out of this gun. And I was kind of inspired by something that Fred Billig and Stanley Mulder tried back in probably the 60s, where they used a cannon to try to shoot a scramjet out of it. So I designed a scramjet. We launched about 10 of them out of this gun, Mach 7 to 9 range, and had 10,000 PSI hydrogen. It was an exciting project. Just being in Livermore and tooling around on a bicycle, all the labs was thrilling. It was really an exciting time. So we flew it several times. The challenge was we had to measure the position with time. We could measure time very accurately. We had access to nuclear technology. It was amazing stuff we had access to. We could measure time more than accurate, but the position versus time was really hard to do. We had to get 1 in 10,000 accuracy. And we tried radars, we tried flying. We had a guy fly over from Holland with his fancy radar, or Denmark or something like that. We flew through metal screens, little metal foils, and we could only get 1 in 1,000. So we got data. The thrust curve was above the 0 line, but the uncertainty band dropped below that line. So I could never conclusively say that we had positive thrust using this technique, but it was still exciting. And by the way, later in time, they actually achieved, Livermore kept working on it. They finally did achieve 1 in 10,000, but we were out of money and finished our project. Okay, I'm going to wrap up talking a little bit. Okay, we are running out of time, but I can do this part relatively fast. So I just want to spend a little time with, that's all the technology that kind of got us here. What have we done to actually fly, right? We took all this technology, and NASA, with the X-43 in 2004, flew for the very first time a scramjet engine that generated net thrust and proved the scramjets work. As Mark Lewis says, it was the Wright brothers' flight of hypersonics, 101 years. We were aiming for 03, by the way, for 100 year, but missed it by a year. You can see a few things. Number one, you can see the dark thrust curve in the green there, positive thrust, net thrust. The green curve, that's the 3 sigma uncertainty band, a lot of uncertainty that I talked about, right? We showed that we could, using CFD, predict what was going on inside of a scramjet engine. You can see the comparison to pressure there. So we learned the hypersonic air-breathing flight is feasible. Propulsion, ground test, analysis can match flight. We really wrung our hands about hypersonics body separation. We showed we could do that. We had the tools to do it. We also learned that you have to be very careful to avoid missing things. The very first flight, which is why we didn't get 03, the control system, the tail control system on the Pegasus booster that boosted this up to hypersonic speed failed, and we lost the vehicle. So attention to detail, very important. This is, I think if I click it, this is a neat old, there we go. So in the lower right, that's a wind tunnel test. So this was actually flying a wind tunnel model. It was literally the same model except the internal structure and thermal protection system on the outside was different, but the same geometry. The engine was identical. It had you see water cooling coming out of the leading edge there. You see, that's the simulation on top showing you the vehicle attitude and the tails, and in the left there you see an infrared camera of the vehicle actually operating on that second flight on March 22nd, 2004. Pretty cool. And then the X-51 about a decade later, where this was the Lindbergh flight. It proved that hypersonic air-breathing flight could be practical. This was not a wind tunnel engine. This was a fuel-cooled engine that if we had recovered it, it could have been used again. And this was an engine that operated, instead of for 10 seconds of Scramjet, it operated for minutes and accelerated from Mach 4.8 to 5.1. One of the learnings was you need to fly a lot, and we should have had more than 4. Sadly, we didn't. The vehicle was designed to fly to Mach 6.5, between 6.5 and 7, and we could have done that if we had had more time or more vehicles to fly. But we again learned that air-breathing flight hypersonic flight is practical. It was designed using MDO, so we proved that MDO works. We learned a lot about vitiated flow. That's when you burn the air and create water and CO2, the impacts that can have on the combustion process. We actually lost a flight because of those effects, at least in part due to those effects, so we had to learn a lot about that. FTSI, that stands for Fluid Thermal Structure Interaction. We experienced some of that on the CAL, and it affected the performance of the vehicle, learned how important that was. Also, integrated system ground testing, critical for success. And again, more vehicles is good. This is actually the first flight. So there were 4 flights. The first flight was partially successful. It had some seal leaks where hot gas got inside the vehicle, and so it was operating, but then was lost due to the internal heating. The second 2 flights had some anomalies that I don't have time to get into, and then the last one was fully successful and did what I described on the last flight. So just briefly, you're going to see it drop here, 50,000 feet, B-52 out over the Pacific headed west. It's being chased by an F-18, again, at the service ceiling limits of these aircraft, 50,000 feet. It's going to drop 4 seconds later. The ATACMS rocket booster comes on, kaboom. Now it starts doing its pull-up. It's heading up to 60,000 feet. And you'll see the rocket booster come off. And you'll see the world's, at least, the world's first Scramjet contrail here in a moment. You'll see a little pigtail come off. That's the booster sep. And right there's the booster, and that's Scramjet contrail. Pretty exciting. That was pretty neat for me through, going from a grad student in hypersonics up to the point where he flew something. So in summary, this is where we're at. We're at the point where we've proven air-breathing hypersonic flight works, and we have operational hypersonic air-breathing cruise missiles at this point. People are working on reusable hypersonic aircraft and even space launch vehicles. It's an exciting time and an exciting future. And I'm still doing it 40 years later, and still having fun doing it. So with that, I'm going to thank you for attendance and your time, and I think we got a little time for Q&A. Thanks a lot.
All right, thank you very much, Kevin, for such an interesting presentation. I just would like to add, over the years that I've worked with Kevin, he's been very supportive and accommodating with his time, not only when we've asked him to provide some testimony up on the Hill about hypersonics, but also out in Orange County, California, where we work together. He's been very giving of his time doing STEM programs for the kids and handing off his knowledge and trying to inspire others. So I really appreciate everything you've done for us over the years, Kevin. So on behalf of AIAA and the AIAA Public Policy Committee, it is my privilege to present you with the 2025 Durand Lecture for Public Service Certificate and Medal. So Chris, you want to come up? And then Mark. And we're going to step over here to the middle.
Yes.
Come over here.
Over here?
Yeah, we're going to do it in the middle, so better lighting, he said. So here you go. Hand this to you. There you go. Mark. All right, thank you.
Thank you very much. Appreciate it.
Congratulations, Count. All right, I think we have a couple minutes for Q&A. We did get some good questions, so we're going to take, and I know people will be jumping off to the next one, but so we did get some really good ones, and some came right up to the top. So why is there so much interest in hypersonics air breathing when hypersonic vehicles such as rockets and ballistic missiles have existed for a while now? Where do you think the interest comes from?
Well, I think it's what I described up above. It's that getting from point to point and do it in an affordable way. I showed the challenges of trying to use rocketry to go from point to point. So yeah, we've used it to get into space. We used it for ballistic missiles. But for someday, humans to be able to travel at revolutionary faster speed. Just think about it. If you fly at Mach 5 over the Pacific Ocean, a 12-hour flight turns into a 4-hour flight. And that can be game-changing. You could actually do international trips in one day. So instead of a 3-day trip to have a couple-hour meeting, you could have a 1-day trip. And it makes that practical. You're flying in a regime where the materials you make the vehicle at are more traditional metals, things that we're used to building, and I think that's the main thing. Yeah.
You'd indicated the OML typically looks like a flying engine. So is an economically viable passenger aircraft really feasible, do you think?
It is feasible. In the last slide I showed, there were a couple of concepts there. One was one that Boeing started to work on back in about 2018. The company had a project looking at the future of commercial travel. And it ranged from urban travel to regional travel to global travel. So I had the opportunity to at least explore the design of a hypersonic transport, just looking at the future, the possibilities. And that design evolved out of that. And we innovated tremendous things in thermal management, inlet design, the engine architecture, nozzle design. We innovated a number of things that suggested to us that it was at least technically feasible. Now, it's a whole other thing to look at the market and the economics, and NASA's been studying that as well. The other image shown there was a study we recently did for NASA, looking at a high-speed commercial transport. Again, looking at where are we at today? What does an airplane like that look like? What are the technologies that make up an aircraft like that? Where are the shortfalls? Where are the gaps? What technology needs to develop to get to that point? And there's also environmental challenges as well. So technologically, I think we're at the point where we could do it. We could, given the money, we could go build one today. Could we meet the market and economic challenge? I don't know. That's challenging, possibly. There are people in the supersonic realm that are attacking that, Boom, for example. So I think there's stepping stones there. So if Boom's successful, then maybe we can step from there to the next level. The environmental one is the one that I think might be the toughest challenge. Airport noise, when you've got these engines, they're low bypass turbofans, they're naturally, thrust is m dot v. I always tell my students, thrust is m dot v. You can affect m dot or you can affect v. High m dot, big fan. Low v, low noise. But you can't take a big fan and make it go supersonic. It's just drag is going to kill you. So you got to have a small fan, that means low M dot, high V means high noise. So there's the noise associated with this. That's a challenging one. When you fly at 40,000 feet, you could use sustainable fuels, recycle the carbon dioxide. Fly at 100,000 feet, that CO2 doesn't cycle. Not only that, water is a greenhouse gas as well as CO2, and water and NOx affect ozone. So there's some interesting challenges that we still have to conquer. And so people are starting to think, how do you do that? I think we're going to need a different energy source than burning hydrocarbon or even hydrogen, because I said water attacks ozone too.
Yeah.
So even hydrogen isn't going to totally solve that problem of 100,000 feet flying, say, at Mach 5.
When you look at a concept that becomes feasible for, let's say, commercial transport, is the follow-on part, the R&M, the reliability and maintainability, is that understanding there as well? The inspections, or is that still another frontier that has to be understood? How do you inspect these? How do you monitor them for?
I think that is another level. And the way I think about it is, we're in this high thermal environment. You can't so I'll give you an example. Let's say you're flying at Mach 5 and you want to open up an air inlet, like a current airplane you flew on here. Outside air comes on board the aircraft and it's used in the environmental control system, right? It's what you breathe and it's replenished. If you're flying at Mach 5 and open up an inlet, guess how hot the air is? 1,800 degrees. When it slows down, inside it's 1,800 degrees. You're going to be cooked in a second. So you're in a very hot environment. You've got to thermally manage that. You got to take that heat out of the air. If a joint were to leak and hot air gets in the vehicle, like we did on the first X-51 flight, you're going to destroy the inside of the structure. So I think it's a whole different level. Yeah. We're going to have the way I describe it is the airplane is going to have a nervous system. It's going to have to set a series of sensors and diagnostic systems that is constantly evaluating the health of key pieces, joints and thermal management pieces and so forth. So if it detects anything going awry, the airplane can slow down to a lower speed where the thermal's not an issue. So it's just a totally different level when you're dealing with that thermal environment.
We've got time for one last one. I want to kind of get back to, we talked about at the beginning, your 42 years. There's a question, can you speak to how you've handled the failures in unsuccessful programs throughout your career? So what have you learned? What have you taken from these attempts? And what have you applied, personally and professionally, I guess?
Yeah, well, I tend to not be risk averse. I tend to like to push the boundary. So it comes with, when you're pushing the edge of the envelope, you just have to know that not everything's going to go perfect. But the thing that I find thrilling is what you learn from it. That's what I take away from it. Mm-hmm. It's not so much it's disappointing, right? The first flight of X-51 had that failure and leak. It's disappointing, but man, what you learn from it, that's what I take away. Mm-hmm. Learn from all those things, because that's that continual learning, that's what makes life exciting. To continue to learn, to grow, to understand the world around us and how to, manage it and tackle it, so.
Wow. Well, thank you very much, Kevin. I want to thank you again for agreeing to do this presentation on a very, very germane topic to what's going on, and remind everybody that there's a lot more to see this week at SciTech, and this presentation will actually be up, I think, later this week on the AIAA pages. So take a look at it again. But thank you very much. Everyone enjoy your rest of the day here, as well as the rest of the conference. Thank you, and have a great day.
Thanks for coming. Thank you. That's awesome.